Part E of Module 3, exercise questions. In this part, we will have 3 sets of exercise questions. Set number 7. Look at our first question. If we can solve a computing problem by both non-recursive, we mean iterative, right? Yeah, iterative and recursive methods. The recursive way usually takes less computing resource. First, the answer is false. Actually, the answer is more computing resource. Why? Yeah, I explain in the notes. Yeah, so here let me explain another time why. Because recursive way usually takes more memory space. Due to recursion. Yeah. Recursion implementation, the programming language needs to do a lot more inside the main memory. Yeah. So in main memory, how to implement recursion. A recursive function needs to call itself automatically, right? A recursive function calls itself automatically. How to make that happen in a high-level language? Yeah. So the idea is using stack data structure. Stack data structure in main memory. Create a stack to implement recursion. Okay? Here, let me use the Fibonacci example. Fibonacci example. For example, yeah, in order to evaluate fibo of 10, you push it into the stack. You don't know the answer. It relies on previous 2 values, fibo of 9, and the fibo of 8. But we do not know its value. So if you do not know the value, you just push into the stack, right? Yeah, push into the stack. Okay, all right. Until you reach the top fibo, of 2. When you calculate fibo of 2, you know, because you have the formula, fibo of 1 plus fibo of 0. Value given, these 2 values are given, so you can find the fibo of 2. With that value, so you pop up from the stack, right? Because the value is known. Yeah. Then you use that one to calculate the next one, and one by one, finally you reach the bottom. In that way, you implement the recursion inside the main memory through that stack. But the depth, you can think about the depth of the stack. Give you the amount of the memory space used in main memory. The deeper the stack, the more memory resource you need to use. So in that way, because we know the memory space limited, right? The memory space is limited. If your stack is too deep, then you will get a, stack overflow error. Your algorithm is correct, but the computer cannot implement the algorithm because you have the problem of overflow of the stack, or stack overflow, right? Another way, commonly used the term stack overflow, right? Stack overflow, runtime error. Some people have this experience, stack overflow, due to this problem. So that's the background behind this question. Okay? All right, Next question. Second question of exercise set 3, Tower of Hanoi problem. We're familiar with that one. Here we are given n disks. We make 127 moves. How many disk moves do we need to make to solve the problem with n plus 2 disks? So for this question, we have two ways to solve it. All right, so method 1. Method 1, so we use the recurrence relation C of n equals 2C of n minus 1 plus 1. That's the recurrence relation. All right, Okay. Now we know C of n equals 127. Okay. Then our goal, we want to find C of n plus 2, right? So let's do 2 steps. The first step, C of n plus 1 equals 2 times C of n plus 1. So equals 2 times 127 plus 1. Okay? 255, right? So the second time, C of n plus 2, another time, recurrence relation plus 1. So this time, 255 plus 1, right? 511, right? 511. So that's the answer. Okay, so that's the first method. Method 2, some students may like to use this direct way because we need to find n first. Then we have n plus 2, then we can use the formula. The formula is based on our result, the number of disk moves for n disk. That's 2n minus 1, right? So remember our solution. Okay, all right. So what is n? 2n minus 1 equals 127. Okay, so that's the 2 to the nth power of n equals 128. what's this n? N equals 7, right? 2 to the 7. 2 to the 7 equals 128, okay? So n plus 2 equals 9, right? So next, 2 to the 9 minus 1. That's the number of moves for n plus 2 disks. All right, so 512 minus 1, still 511. You can see these two methods, both we can find the solution. Yeah. All right. Okay, yeah, so that's the second question. The third question. The recurrence relation. So this one corresponds to our, what that question? Binary bits problem, right? Yeah, so this corresponds to our binary bits problem. All right. So here, the question is, this recurrence relation can only have a solution when n is power of 2. In other words, if n is not power of 2, then it cannot have a solution, right? No, that's the statement of this question. Yeah. So the answer is false. Yeah. Because we know when n is not power of 2, we can still find a solution. Yeah. So in our lectures, we did it. We solved it. Yeah. To do it, there are two methods. Yeah. Two ways to do it. Yeah. Here, I just review a little bit. Two ways. The first way, guess and verify. Verify. Okay, guess and verify method. All right. The verify part, mathematical induction. Mathematical induction. Okay, yeah. Second way, yeah, I hope you can get this one. Smoothness rule. Okay, yeah. Smoothness rule. Yeah. Because for power of 2, you need to get power of 2 solution first. Okay, yeah. So here I just call special solution. Special solution, we have 1 plus n, right? Yeah. So that's power of 2. All right. So then when we go to the general case, we know that should be an integer, so we put a floor function. All right. Yeah. After that, in order to apply the smoothness rule, how do we apply the smoothness? How do we apply the smoothness rule here? Here, we need to show this function is a smooth function. But not calculus smooth in our algorithm context. So we need to check if the function 2n is contained in this asymptotic notation class, then it is smooth. Okay, yeah. We need to check that condition. Then we have the smooth function, then we can apply smoothness rule. Okay? Yeah. Here, just a review of the two ways we can use to solve this problem. All right, so we finish our E.1 video here.